Hello everyone, my name is Masanori Maeda from Soka University of Japan. Today, I would like to talk about evaluation of non-invasive swallowing test device using Hetero-Core fiber optic pressure sensor. In Japan, many elderly people have pneumonia, especially aspiration pneumonia caused by dysphagia is a serious issue. The ratio of aspiration pneumonia to total cases of pneumonia increases as people get older. In medical organizations, video fluoroscopic swallowing study (VFSS) and video endoscopic swallowing study (VSS) have been widely used for examining swallowing disorder. For the VFSS, the state of the esophagus was examined using contrast medium and a camera during swallowing. For the VSS, the doctor examined directly the esophagus using an endoscopy. However, these examinations require medical staff and patients to visit the clinic and invasive for the elderly. Considering the increase of domestic care due to aging and diverse care needed, the swallowing examination instrument is preferable to be comfortable, portable, cost-effective, and easy to use. Usually, after eating or drinking, the eating lamp goes into the stomach through the esophagus. The epiglottis has a function of covering the trachea when swallowing, preventing the food and drink from entering the trachea. When people get older, the thyroid cartilage moves slower, so that the eating lamp goes accidentally to the trachea. A decreasing swallowing function with natural aging may cause pneumonia. Therefore, it is important to detect early abnormal swallowing. Thyroid cartilage moves up and down in conjunction with the movement of epiglottis, so it may be possible to evaluate the state of swallowing function from the movement of thyroid cartilage. In our laboratory, as a swallowing test device, an optical tape-shaped sensor was proposed. As shown on the picture, the Hetero-Core optical fiber was embedded in a medical film tape. The tape-shaped sensor measures the stretch of the skin during swallowing by attaching to the skin surface of the laryngeal prominence. The tape-shaped sensor indicates that the movement of the LP can be detected using Hetero-Core optical fiber. The structure of the optical fiber will be explained later. However, the fiber optic tape-shaped sensor has a risk of skin tear to the elderly with weak skin. Therefore, it is preferred that the device is not directly attached to the skin surface. So, we evaluated a non-invasive swallowing test device using Hetero-Core fiber optic pressure sensor. I will divide my presentation into two contents. The first content is swallowing motion test, and the second one is the evaluation of response to swallowing motion. The Hetero-Core optical fiber is made by inserting and fusion optical fibers with different core diameter, different fiber optic transmission line. As the Hetero-Core portion bends, optical loss changes can be observed. By using the Hetero-Core optical fiber, we can detect movement through observing optical loss, so it can be used as a potential physical motion. This figure shows the structure of the Hetero-Core fiber optic pressure sensor. The Hetero-Core fiber was put between a silicon rubber with a convex part in the middle and a UV resin with a concave part in the middle. The size of the fiber optic pressure sensor was 400 mm square and 4.7 mm thick. The silicon rubber is soft and easy to be deformed by pressure on top. The Hetero-Core portion was set to be under the convex part so that when pressure was applied from the top, the hetero-core portion will be curved. Depending on the curvature, the optical loss will also change. As a result, the sensor detects pressure by observing the optical loss change. Next, in order to use the pressure sensor directly on skin, we propose the following swallowing test device. This device is structured with a hetero-core fiber optic pressure sensor, an outer frame by 3D printer molding, and a puff. A puff was put on the pressure sensor in order to decrease the feeling of oppression and to fit well on the skin. The shape of the outer frame was designed to fit the subject's neck. The swallowing test device was installed on the subject's neck to detect change of pressure by the movement of LP. Next, we conducted the swallowing motion test for 5 subjects of different genders and body type as below. And we evaluate the result of the device's research response for each subject. And next, we will explain the setup to swallowing motion test. A surface myoelectric potential of the genohyoid muscle was measured as a reference signal using an electromyograph, abbreviated as EMG. The genohyoid muscle serves to move the LP. The swallowing test device was put 1 centimeter above the LP by hand. The optical loss of the hetero-core fiber optics was measured with an LED light source with a wavelength of 1.31 micrometer at a sampling frequency of 30 Hz. In the swallowing test, subject kept 3 ml of water in his mouth for 10 seconds and then swallowed the water. This operation was repeated 3 times. This is video of the swallowing test. The optical loss changed at the same time as myoelectric potential. And this figure explains the definition of the swallowing time. First, a rough swallowing waveform was selected by the EMG and the video. The baseline was taken from the peak. The threshold was defined by the 10% of the peak. The start time of swallowing was the time when the optical loss was exceeded at the threshold. And this table shows average and standard deviation of swallowing time for each subject. We can find 2 results. First, a female standard deviation was larger than male one. Second, male whose LP cannot be seen has larger standard deviation than male whose LP can be seen. First, I will talk why female standard deviation was larger than male one. Left figure shows male subject signal and right figure shows female subject one. Upper is optical loss of the test device and below is RMS for reference. As shown in the peak of optical loss, the height of the peak was about less than 0.2 decibel and 0.02 decibel, respectively. It is said that female peak value was smaller than male's one. This may be influence of the difference male and female development of the thyroid cartilage. Additionally, we found a characteristic in this female subject signal. Left figure are female subjects, optical loss and RMS, and right figure are the second trial of subject D. As shown in the right optical loss, some signals with unstable baseline were observed. This is probably due to the shaking of the hand that holds the test device, and therefore, male subjects with low peak values and unstable baselines are expected to have a higher standard deviation. Next, we discuss the reason why the standard deviation of the subject whose laryngeal prominence was not visible was larger than that of the male subject whose were visible. Left figure shows waveform of male subject B, whose LP was visible, and right figure male subject B, whose LP was not visible. Upper is optical loss of the test device, and below is RMS for reference. As shown in right waveform, subject C's baseline was unstable due to the shaking of the hand that holds the test device. This is summary of my presentation. In conclusion, the proposed test device may be effective for male subjects whose LP is visible. Thank you for listening.